Hi, in this video we're going to be talking about neat proportions that show up inside triangles. One of them is if we have a side that is parallel to one side of a triangle. So we assume that these two are parallel with each other. What that does is it breaks our triangle up into these nice proportionate segments. So we get this little piece that's up on the top, and the little piece that's up on the top down here is going to be proportional to these other pieces on our triangles. So we kind of get these little chunks in between the uh, parallel lines and between the parallel line and the top. Save this one for a little bit later once we see another theorem. So skip this one for now. We're going to jump down to these examples. So down here on this one, this looks exactly like the diagram up top. We're able to make a little proportion using the two small bits that are up on the top, this 8 and that 6. And that's going to be equal to the two bits that are on the bottom. And we're able to do that because of these parallel lines and the proportion stuff that it makes. So 10 and x. And so now I just want to solve that proportion. Now I don't like that x is in that denominator. So I'm going to flip both sides. So I'm going to make this 10 over 8 equals x over 6. And then I can just multiply both sides by 6, and I'm going to be finished. So x equals, let's see, we got 60 divided by 8. I could simplify that fraction a little bit because I'm feeling frisky. I'm going to divide them both by 4, so I get 15 over 4 for my answer. Now, the cool thing is this property actually works even if you don't have a triangle. Just like we kind of had these two top bits, these two bottom bits, there's nothing to say that this wouldn't work even if it's just parallel lines. So we can do that same thing again. We've got, and I'm going to do these two bottom bits first. So I'm going to grab 6 and x, and then grab the two top bits. So that's 5 and 4, 4 and 5. And then I get a little proportion that I can solve. So equals and proportion. And I'm going to solve it the same way. I am going to flip both sides. So I got 6 over 4 equals x over 5. I can multiply both sides by 5. And I get 30 over 4 equals x. Simplifying that fraction, I can divide top and bottom by 2, and I get 15 over 2 equals x. It's that quick and easy. You grab the two top bits, they stay on top. The two bottom bits, they stay on the bottom. Now this next theorem, we're going to kind of draw together. So we've got a ray that bisects an angle. So I'm going to draw this ray down here that bisects this angle. I'm going to say it bisects at point D, and it's making these two angles congruent. If a ray bisects that angle of a triangle, it divides the opposite side into two segments. Yeah, it does. It makes this segment here AD and another segment over here DC. Now, those two segments are proportional to the other two sides of the triangle. And I do want the other two sides. So what that means is if we make like a little fraction with AD and DC, the two sides that kind of got split up, that's going to be equal to the other two sides of the triangle, the ones that match with our bits. So we've got this AB over here and our BC over here. So we can say that's going to be the same as AB over BC. So we cut this thing in the bottom in half. That makes a little ratio, and that ratio is the same as the sides on that side of the ray that bisected the thing. Let's try it out. So in this example, we can see we've got that angle bisector there, and that's chopping this thing on the bottom in half. I can already tell that 6 and 8 are kind of like that green and that blue pieces from the diagram that I've got above. So that is going to make a ratio. The other ratio is being taken from this bottom two pieces. One of them we know already, and that's the thing that we're trying to solve for. So I'm going to put x on top and the red one on the bottom. It doesn't matter what order you put those two in, just as long as you make sure it matches on the other side. So orange and blue matched up, so 8 is going to be on the top, and then that 6 has got to be on the bottom. Now this red piece here is a little tricky because I don't have a number there, but I know this whole length is 10, and some of it got used up by that orange piece. So the whole length on the bottom is 10, but I don't want to use the whole length on the bottom. I've got to take away however big x is. I don't know how big x is, so I'm just going to write x. So I've got 10 minus x equals 8 over 6. These two are across from each other, and these two are across from each other. And our two pieces that got bisected in the triangle are together, and our original sides of our triangle are together. So to solve this thing, I got to get x out of the denominator. So I'm going to swap these two diagonals and make it x over 8 equals 10 minus x over 6. And then I'm going to multiply both sides by the least common multiple of those two fractions, which is 24. I could cross multiply, but I'm not a fan of cross multiplication, so I'm not going to do it. 24 divided by 8, that is 3. So I've got 3x equals 24 divided by 6 is 4. So I've got 4 times that 10 minus x. Don't forget those parentheses around the numerator that are understood in proportions. Distributing the 4, I get 40 minus 4x. And then I'm going to add the 4 to both sides. And we can say 7x equals 40. The last step is just to divide both sides by 7. So x equals 40 over 7. That's done. All right, now my paper is double-sided, so I can show both of these theorems in order to work with this one. So it might be a little bit of flipping. If you wanted to, you could redraw the diagram of here over to here too on your notes, up to you. But we want to try to complete these proportions using these two theorems. So if I'm using this one, I'm looking at RS. So RS is right here, JR, which is right here, and then KJ right here. So this is using this angle bisector. And in that angle bisector, it's saying that, hey, if you're using these two little bits that got cut in half from that angle bisector, then these two have to be proportional to those two bottom bits. So RS and JR are on the bottom, or are on the top. So KJ and KS has to finish this proportion. It's shifted a little bit from where we have here, but you can like swap diagonals just like you can with any proportion. In this one, I've got QL and PM, and then I'm also looking at SQ right here. So this one's using the side splitter, where we've got these two pieces of kind of like this overall triangle, and then these two pieces of this overall triangle from those parallel lines. So the other piece that matches with SQ, just like PM and QL, must be JP. Next, I've got KL and LW. So let's see. KL is this whole piece here, and then LW is this little piece right here. And then MW is the other thing that I'm looking for. So KL is this whole piece. Yeah, let's draw it. So we got this whole side, and we've got another side splitter. So it's doing the same thing that this little blue piece is going on. I said side splitter, but I meant angle bisector. So I must need this other piece that's over here. So KL and LW, and then MW is on the bottom, so I must need that other big piece here. So that's KM. Final one uses SQ again. So here's SQ and JK. So that's over here. And KS. So that's right here. So this is using another one of these side splitters, where if we just complete it with this JP right here, we're going to be set. And that is it for our video on these proportions in triangles. So if you've got a parallel line, it divides top and bottom proportionally. If you've got an angle bisector, it makes proportions with the two pieces on either side of that angle bisector. Thanks for watching. Bye bye.